Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to my next session of my presentation. And my presentation title is How to Perform a Reliability Assessment of a Generation Substation Equipment or Proponent Facility Equipment in the oil and gas industry. My name is John Kweku Amoto, and I'm a professional electrical engineer for 30 years, and I'm based in the United States of America. Next, on this slide, I will talk about the outline of my presentation. And the first thing we'll talk about is performing asset reliability assessment. Is it a project or a major task? So, based on the analysis that we'll see on the slide, we'll basically come to a conclusion whether we are performing a project or basically implementing a major task. Next is identification of the list of equipment that reliability assessment will be performed. And this is usually provided by the reliability department from your department. And also other departments that you have. If you have an asset management department, they can also provide you that list. Next is identification of the required and applicable standards that you need to use. Performing reliability assessment, there are basically engineering standards, industry standards, benchmark standards, and also internally you should have a procedure and guidelines that you need to use. Then identification of all the stakeholders in the team. That's very important. Basically forming the team and the selection of the skills of your team to be able to help you with your reliability assessment. And also setting up a kickoff meeting with all the stakeholders in your team. Then collaboration with all field engineers and proponent engineers to obtain the documentation and data that you need to perform your reliability assessment and also your analytics. Obtaining the risk score and the risk costing data that can be obtained from your reliability department or your asset management department. Then also, performing the reliability assessment itself. That can be basically, based on the dates that you schedule with your field engineers to perform the reliability assessment, collect all the required data that you need. Then after that, you do all your data analytics and write your good report. And your good report should come up, identify all the gaps that needs to be implemented, and the required corrective actions that needs to be implemented. And with regards to the corrective actions, that has to be feasible. So that itself requires basically sending a copy of the report to your stakeholders for them to have the ability for them to review what is in the report and also the corrective actions, because they also have a hand or a say in the corrective actions. As much as you are enforcing the corrective actions needs to be feasible. Then the last part on the list is having a closure meeting with all your stakeholders. So that is when all the agreed upon what is in the report and also the corrective actions, what has been agreed upon, and basically that will be further discussed and implemented. And the corrective actions will be assigned to the individuals. Like I said, the individuals that the corrective actions has to be assigned has to agree upon that. It has to be the correct person that needs to implement that corrective actions. Okay, so on this slide, remember I made mention that performing a reliability assessment, is it a project or a major task? Okay, so we'll see whether it is a true statement or not. Okay, so I'll say it is a true statement. When you're performing reliability assessment, you should basically have the notion that you want to implement it as a project or a major task and not just as a task. So it should follow just like a major project. It should follow basically the project life cycle, and it should have an initiation and definition stage where the scope of the reliability assessment is basically defined and discussed with all stakeholders. Then you need to identify your resources, manpower resources, especially in regards to operation and maintenance that will provide that support to you during the day that you are performing this reliability assessment and collection of data. Then especially the one that will perform the especially for a power transformer, the one that will perform the oil gas sampling collection of oil for AGA, and also performance of infrared thermography. You should identify all those resources and discuss with them what you intend doing, and basically what you are going to do with the reliability assessment. Then you need to identify all your stakeholders, and basically we'll see the list of stakeholders that you need to identify on the upcoming slide. Then you need to form the team, and forming the team, basically you need to identify all the different disciplines of engineering that you are going to interact with. And also forming your team, you need to identify the skills that is needed, right, to perform reliability assessment. Then you need to identify the schedule, right? Okay, so you come up with a date. The date has to be feasible with your proponent that you are interacting with. Their operational schedules, maintenance schedules has to basically be has to fit in with the date that you select for to perform this reliability assessment. Next is the planning piece, right? And the planning piece basically involves collection of documents and data. Just to mention, just for the electrical side, but you know, for other reliability assessment of other equipment, basically you might need more than that. You know. So for the electrical side, let's say you will need 1 line, 3 lines. Then you also need a maintenance history and inspection test reports. Basically, this should be in a repository or archive drawing database that you can obtain all this information. Then OEM drawings. All of these equipment come with OEM drawings, and basically you can obtain them. A lot of these drawings are probably in an archive of repository of database. Excuse me. Next is the execution piece. That is when basically you go to the field on that day with your personnel to perform the field data gathering and analysis. Then basically analysis of your maintenance and operation records. So basically your maintenance history and inspection and testing records that you collect from the planning phase of you performing this reliability assessment. That is the execution stage is when basically you go through all those documentation and analyze the maintenance inspection and the testing for each of them, and basically identify all the gaps. Next is the drafting of the report piece, and basically identify, after you identify all the gaps, you need to come up with corrective actions for the gaps that you have identified. And coming up with the corrective actions, it requires a discussion with all stakeholders, and especially the facility. They have to take a look at the corrective actions and the ones that you assign the corrective actions to, and the feasibility part of the corrective actions. Next is scheduling the closure point. Basically scheduling of the closure meeting to discuss the contents of the report and the corrective actions. That has to be done in a very well coordinated manner. Next, let's talk about the types of maintenance strategies that we have over there. I mean, we have a myriad of maintenance strategies, but let's basically talk about the ones that are applicable to most of generation plants and industrial facilities. So the first one is predictive maintenance. What is predictive maintenance? Predictive maintenance is basically when you collect oil analysis and basically perform oil quality testing and also dissolved gas analysis to determine basically the components of your gassing that you have in oil. So that can be considered as predictive maintenance. Another typical predictive maintenance is infrared thermography, basically when you perform infrared thermography to identify hotspots of electrical equipment. That is considered predictive maintenance. So implementing predictive maintenance basically can be scheduled based on frequency. For instance, infrared thermography can be scheduled like every 6 months, every 1 year. That is based on the maintenance philosophy of the company or the utility company. And oil analysis, for instance, can be scheduled every year for typical power transformers. Run to failure, that is the most cheapest form of maintenance strategy. And Most often than not, it is tied to non-critical equipment. So basically, if you have for instance, if you have a motor that basically it's non-critical, small size motor, basically you can consider it around to failure, and basically because those motors can be replaced easily. So one of the caveats that basically is tied to run to failure and maintenance strategy is you should have a lot of spares. So that itself basically pushes the envelope of your spare inventory in terms of having a lot of spares. So that itself is additional cost. And you also have to think about the shelf life of these spares that uh, you basically have in place, and also your inventory cost. Next is the time-based maintenance. This is most often the type of maintenance strategy that has been implemented by most utility and most industrial facility, right? So that itself is based on performing maintenance at a fixed interval. So let's talk about power transformers. Power transformers are basically, most often than not, time-based maintenance is performed every 6 years. So basically, you have a maintenance strategy in your planning asset management software, basically that basically triggers that maintenance to be performed every 6 years. So basically, it requires a shutdown. That is when audit, inspection, and electrical testing is performed for the power transformers. And also, at that time, depending on when DGA is performed, if it is more than 1 year, then that will be the time that before the shutdown, you collect the oil samples for oil quality testing to be performed, and also dissolved gas analysis to be performed on the power transformers. Next is corrective maintenance. Corrective maintenance comes in on a daily basis, or let's say when you are performing the time-based maintenance and you identify a component of the power transformer that needs to be repaired or replaced. So that is when corrective maintenance comes in. So on a daily basis, basically as a maintenance engineer, and basically you are in charge of basically substation assets. If you should basically receive basically a component that is defective, and basically you have to put in the required maintenance request and basically material requisition to replace that component of that equipment. That is called corrective maintenance. So corrective maintenance comes in anytime, on a daily basis, or maybe during a time-based maintenance. Next is condition monitoring. Condition monitoring is when you put in a monitoring device to monitor the equipment or component of the equipment. So let's talk about the power transformer, right? If you have a bushing monitoring that is in place, that monitors the leakage current, that monitors the capacitance C1 and tan delta of the C1 region of oil impregnated type of bushing transformer or condenser, or C2 region and tan delta of that transformer. That is considered a condition monitoring. You can also have a condition monitoring in place that monitors the condition of the on-load tap changer. So basically, it's monitoring the taps and also the oil condition of the transformer. Next is condition-based maintenance, right? Condition-based maintenance basically goes a little bit beyond that. That itself is based on a list of factors, right? Okay, so you implement that basically to change the time-based maintenance for this equipment. Let's say you have a power transformer, right? That has been slated for time-based maintenance of 6 years, right? And you are implementing a condition-based maintenance. Then a lot of factors comes into play. The criticality of that power transformer, the safety part of that transformer, the consequence of failure of that transformer, the type of customers, critical customers that transformer is feeding. So all these factors comes into play for you to implement a condition-based maintenance, so that basically you can extend. That allows you to extend the time interval for these for performing maintenance on this transformer. So basically, based on the condition, for a 6-year time-based maintenance for a transformer, you can extend it to 12 years, to 10 years, to 11 years, based on, or basically, reduce the time to 3 years. So it's all based on the condition, and that is based on after you have performed a condition assessment of that transformer and have implemented a scoring scheme based on different list of parameters and weights that has been assigned to those parameters. Next is reliability-centered maintenance. What is reliability-centered maintenance strategy? Okay, so that one is an optimization. You're optimizing the implementation of all these types of maintenance that I have mentioned. That is predictive maintenance, run to failure, time-based maintenance, corrective maintenance, condition monitoring, condition-based maintenance. So you are optimizing that, and based on the list of criteria that I've made mention, that is based on the criticality of that equipment, the safety part. Let's say if that equipment should fail, what is the consequence of it? The safety hazard that is going to create. Then also the customers that equipment is feeding, the critical customers. So all these criticalities has to be identified and reviewed for you to successfully implement a reliability-centered maintenance strategy. In implementing the right type of maintenance strategies, what are the criteria that you need to consider? Okay. So the first one is the criticality of the asset, right? If you, for instance, I always like selecting the power transformers as an example. If you have a power transformer, right? How critical is that power transformer that you are basically deciding on a maintenance strategy? What is the consequence of failure? The consequence of failure, I'm talking about the safety part, the hazard that is going to create, the environmental spillage that is going to cause. Then also the economics of that failure, how much loss of revenue that is going to create. Then also, do you have redundancy in place? Okay, for instance, if you have a particular transformer, right? Do you have another transformer that basically, if one should fail, you should have an N-1 contingency that will provide that reliable power to your customers. And what is the condition of that N-1 transformer? Is it in good condition? So these are all the factors that you need to consider. Next is installing of condition monitoring device and technology. Okay, so if you have a condition monitoring device in place, let's say a pushing condition monitoring device in place that monitors the leakage current, the capacitance of the C1 region, the tan delta of the C1 region, the capacitance of the C2 region, and tan delta of the C2 region. And also you have an online monitoring device that measures just 2-parameter oil quality, that is moisture. And DG, let's say if you have a 2 gas, 5 gas, 7 gas, 9 gas. So if you have all these monitoring devices in place, right, that helps you to identify the type of maintenance strategy. So that itself basically helps you to extend the maintenance interval based on the condition parameters that you are receiving in your state-of-the-art SCADA systems. Just to mention a few, these are the type of substation equipment. So like I said, if you have a generation facility, you should have motors, switchgears, generators. So the list that I have is just for main substation or Proponent distribution and substation. So you should internally have an internal inspection checklist. Okay, so but on the slides that are coming, I'll show you what you should have on your internal inspection checklist. Right, that itself will help you to basically perform your visual inspection on that day that you are going to perform the reliability assessment. and also help you to collect your data that you'll use for your analysis. So you should have an internal inspection and checklist for power transformers as an asset, and also high voltage circuit breakers as an asset, medium voltage switchgear as an asset, battery systems and chargers as an asset, and gas information and insulation systems as switchgear as an asset. Okay. Next, it's identifying your stakeholders, right? What are your stakeholders? Your stakeholders basically stems from your upper management, all the way from your VP, your directors, your engineering managers, your discipline engineers, and all the component engineers, and also your operation and maintenance staff. And also, if you have basically a specialty group, you can tie them in as well, because that is very important. Because if you perform in especially protection engineers and also consulting engineers, you can also tie them to as part of your stakeholders. So this is just to mention a few for your stakeholders: proponent engineering manager, proponent maintenance manager, proponent engineering director, and maintenance director. Then proponent field engineers. And proponent field engineers, you can have discipline engineer and operation engineer. And for the specialty group, we'll need a protection engineer and high voltage engineers and consultant structural engineers. Because the reason why structural engineers comes into play is because of some of the foundation that the equipment basically is located on. You need to assess that foundation, right? If you have a transformer that has been basically in operation for about 40 years, sitting on this foundation, basically weakens, especially stock of these transformers, basically, and cyclical loading of the transformer basically weakens the foundation. So the foundation itself has to be assessed, right, by a qualified structural engineer. Then also, you should have asset and reliability engineers and field maintenance engineers as well, and field operations technicians, crafts that will provide basically the required score on that day that you perform the reliability assessment. And actually, they're the ones that will perform the infrared topographic survey as you are moving, performing your reliability assessment. Then your maintenance craft, right? You need electrical technicians and relay technicians as well on that day that basically. And they also will provide you a lot of the documentation that you need, especially the maintenance records. Sometimes, you depending on the setup of the organization, sometimes you can have the maintenance craft rather giving you the maintenance inspection electrical testing of these equipment. And sometimes you can have an engineering repository where all these documentation are located: inspection, electrical testing results, and also engineering drawings, and OEM documentations, maybe located in these repositories. Yeah, so it all depends on the setup of that organization. Then also material requisition and procurement, because once you identify the gaps, then comes the corrective action sheets, right? Okay, so maybe you might identify a gap that requires a purchase of a component. Let's say if you have an oil temperature indicator that is defective, right? Basically, then you need to replace that. You need to create a corrective actions that will replace that component. If you have a widening temperature indicator, if you have an oil level gauge that is defective, you will need a material requisition procurement for that. Next is setting up a kickoff meeting. That is also one of the important pieces of reliability assessment, right? Okay, so you need to set up a kickoff date for the reliability assessment. That is basically the beginning part of the reliability assessment, and that date basically has to be convenient for all stakeholders. Once you identify the stakeholders, then you send them an email and basically let them know that this is the date that basically you want to perform the kickoff to discuss And basically, you should have an agenda that needs to be discussed during the kickoff meeting. So, and also you need to send the agenda items to all the stakeholders for review before the meeting. Because what it is if you send them the agenda that you have, sometimes they might have basically a feedback to your agenda. They might have other um, agenda items that you might not even think of, and that itself helps with them the lessons learned process, improving on the way you perform reliability assessment as a maintenance engineer, or as a discipline engineer. And typical agenda items are basically you come up with a list of equipment that reliability assessment will be performed on. So after you come up with that list, you have to show them the need, why reliability assessment needs to be performed on this equipment. So you need to show them the list that was given to you from your reliability department or your asset management department, and basically support them with the necessary, provide them with the necessary data, right, that support them. And a particular example is, let's say, it's based on the operating parameters of this equipment, or the last time reliability assessment was performed, and basically it's time to perform the next one. So these are some of the examples of documentation that basically you need to provide it to your stakeholders, because they'll be asking you, why do you need to perform reliability assessment on this equipment? Why do you need, So, and as a professional engineer or as a discipline engineer, you need to have data to support that. Next up, you need to identify your operational engineering and maintenance support. You need to bring it to their attention that when you are going to perform the reliability assessment, you will need that resource, right? Okay, so it is at this point that you make them aware that so they will also on their side start planning to provide you that support. There shouldn't be any sticker shot on that, because when you request for that at the last minute, then it's going to be very difficult for them to provide you that support. So it is very much better to ask for that support very early, let's say 2 to 3 months before the scheduled date, so that they can also, it also helps them with their planning from their side. As part of the reliability assessment, right, because reliability assessment is performed when the equipment is energized, right, is in operation. So it is at this point that you perform the infrared thermography, right, and you need a certified thermography person to perform that to identify hotspots. And you'll be amazed. I've basically run into basically hotspots during whilst performing reliability assessment, and this is something that you wouldn't even know. You'll be waiting for the next calendar year or 6 months or 1 year to perform the infrared thermography on that equipment. And you'll be surprised that it was during when we were performing the reliability assessment that is when we identified those hotspots on those equipments. Then it is at this point that you need to ask them, is there any site-specific training that is needed? Because you'll be entering a lot of these industrial facilities, right? Okay, refineries, etc. And basically, there are hazards there, and part of it is basically to work with the EHS safety hazard operations department to identify, ask them about any site-specific training that will be needed by you or any other person that is part of your stakeholders, your team that is performing the reliability assessment. So you also have to ask them, do you need to perform the site-specific training a day before, or basically on that day that you need to perform the reliability assessment? Next is the collection of the documentation piece, right? Okay, so sometimes it all depends on the setup of the organization, right? Okay, sometimes you can have the repository where those documentation are located in the engineering side, right? And sometimes you can have the repository on the maintenance and operations side. Right? Sometimes too, you wouldn't have digital copies in the repository, but you can have hard copies that will be residing with maintenance and operations side. Okay, so it all depends on the setup of your organization. Right? So that is something that you need to find out where those documentations are located, and you need to basically just it is during this meeting that you need to let them know, component engineers, support engineers, maintenance operations staff too, and give them the list of documents that you need. So right after the meeting, then they will start looking for those documentation for you. And typical examples is what I've listed here, and that is OEM instruction manual, OEM operation manual, OEM maintenance manual, maintenance history records and documents, operational history, and a lot of operational history comes from the operation department. We can get you that list there based on the equipment tag or ID. Then any critical spare list that you have, for a power transformer, right, a critical spare list that you can have will be for bushings, right? And you should identify the amount of bushings, at least for a transformer, you should have at least one bushing for the high voltage side and another bushing for the low voltage side as your critical spare. And for another critical spare component is your oil temperature indication and winding temperature indication and sudden pressure relay if you have a low pressure relay device. And sometimes, depending on the location of the substation, right, and also the criticality of that transformer, and the criticality of basically the customers that it feeds. Sometimes, you can have a capital spare for, let's say, if you have, let's say, 5 or 6 substations that are very in close proximity to themselves, right? You can identify, and depending on the design and the rating of those transformers, you can have a capital spare that will be a spare for these transformers if any of them should fail. So next is also that is when you take a deep dive into performing this reliability assessment. So you should have your field engineering, component engineers to provide the following. I think I made mention in the previous slide that is planning records. If you have SAP as your planning software, right, it should show you the dates that maintenance was performed, and when will be the next time that maintenance will be performed. So once you see those dates, that itself tells you that maintenance is being performed as it's supposed to. And if maintenance wasn't done when it was supposed to, there has to be a reason why. So that is when you need to investigate and find out why maintenance wasn't done as it was supposed to. Then I indicated that you're supposed to obtain the maintenance inspection, testing records, operational records, fault records, OEM operational manuals, OEM maintenance instruction manuals, and spare parts inventory. Next is the standards that you need to perform reliability assessment. Performing reliability assessment is tied to standard itself. Okay, so you have ISO 55001, ISO 55002, ISO 55003. Okay, so basically you should have a standard or a procedure or a guideline that has been basically reproduced out of these standards. So that is based on what guideline you have, your company has, based on what ISO has, and that should be applicable to substation assets, generation assets. But you should also have IEEE, IEC standards for all equipment. A typical example is what I have here, and that is power transformers, high voltage circuit breakers, medium voltage switchgear, battery systems, chargers, gases, related switchgears. Next is engineering standards. Right? Very, very important that because you have industry standards, that is IEEE, IEC, ISO standards, right? Okay. You should also have an engineering standards that your engineering department should have, right? And a lot of these standards are basically a replica of what is in the industry, right? They basically evaluate the applicability of data industry standards, IEC, IEEE, ISO, and basically write their own engineering standards, like I indicated, based on the applicability. Then they will also, you can also have a procedure or guideline, right, to perform reliability assessment. So that is very important. So that's one of the documentations that I developed, when I was performing this reliability assessment, is to come up with a guideline. Because if you have a guideline and a procedure on how to perform this reliability assessment, what it does is, it helps young engineers. That's the first and foremost, that are learning how to perform reliability assessments. They don't need to basically reach out to experienced engineers, experts, for to ask them, basic questions. So they will just straight off the bat start using the guideline. And if they have any question in the guideline, that is when they can reach out to you. Having a guideline itself also, with regards to the quality piece, right? It helps you, and it helps it gives a checklist on what needs to be done and everything. So basically, it helps with the streamlining of the process of basically performing reliability assessment. Okay, so on this slide, remember I made mention that to perform a reliability assessment, one of the documents, and that should be an internal document that you should have, is to have a visual inspection and field data collection sheets. That is very important because that is the check sheet that you utilize in the field on that day that you are with your team performing the reliability assessment. Okay. So it is at this point that basically you also leverage on that and basically train younger engineers on how to perform reliability assessment. As young as they are, basically they have a guideline in place. You develop the guideline for them, but having a field experience, on how to perform reliability assessment with you is also very important, and that helps to sharpen their skills as well. Okay, so this is just to mention the list. What should be on that inspection checklist and field data collection sheet. Okay, so um, an example that I gave here is for a power transformer, right? You should have the nameplate data, and that should be your MVA rating and the cooling class. Okay, so the MVA rating is basically the nominal rating of the transformer and the maximum rating that is given in an MVA. Right? Okay, so, and the reason why a power transformer is rated at the MVA, if you can answer that question. Okay, so the answer is basically when a transformer is rated at MVA, not megawatts, is because when it is connected to a load, the load power factor changes. Right? It is not like a generator, or it is not like a motor that is coupled to a load that has a constant power factor. So as you can see, a motor is rated at horsepower or basically megawatts. So that is the reason why the transformer is rated at rate. Next is the cooling class, right? Okay, so you have owner class. Owner is oil natural. Okay, so the oil is flowing naturally. It doesn't have any force in it. Then AN is air natural, right? Okay, so the air is also flowing on the radiator naturally, right? Okay, so the radiator doesn't have a stage fans located on it to basically remove the heat from the oil. Right? So for a typical transformer, you have two ratings for owner and owner. Sometimes, depending if you have a bigger size of transformer, you can have owner 1, owner 2. So that itself tells you 3 stages. So you have 3 MVA ratings, one for the owner, one for owner 1, another one for owner 2. Right? So on-off-1 is basically the first stage cooling. So you have many fans on the transformer right here, right? So the first stage cooling set of fans will come based on the load, the increase in load from the on level to the on-off-1 level. So that is when automatically the fans come. So then the next one is on-off-2. So that is the second stage cooling. So that is when you pick up more load, and that is when automatically, based on the amount of load that it has picked up, the second stage fans come. Next information that you should have is the voltage rating of the transformer. For the voltage rating, you have the primary side and the secondary side. So let's say for a transformer that has a high voltage rating of 115 kV, 230 kV, 345 kV, and for the low voltage side, you can have 33 kV, 13.8 kV, 4.16 kV. So that's a typical rating for the transformer. So let's say for 115 kV, 13.8 kV, you have 115 kV slash 13.8 kV. That basically designates your primary side voltage rating and your secondary side voltage rating. Next is your current rating, right? As you can see, your current rating is going to be many because it's going to depend on the tap position, right? And also, just to make mention to your voltage rating, you can also have a voltage rating based on the de-energized tap change-up rating and on-load tap change-up. So we'll come to that. Next, your impedance rating piece, right? Okay, so as you know, the impedance rating is usually calculated based or designed and tested based on the owner, the base. So you should have that impedance rating to be provided by checking it in the field. Next is your de-energized tap changer rating. Okay, DETC is de-energized tap changer. What does that mean? Okay, so for this tap changer, the transformer has to be de-energized before you can operate it. It is usually it changes the taps on the primary side for an AC-rated transformer, right? Okay, so for usually the taps are about 5, right? You see it A, B, C, D, E. So for tap A, the voltage indication is different. B, the voltage indication is different. C usually is the nominal voltage rating. Okay, so for 115 kV rating transformer, you see that the nominal tap C will show you 115 kV. Right? Okay, so tap D will have a different voltage rating. Tap C will have a different voltage rating. Okay, so you have a different current rating for all these taps. Right? So that is why I indicated. You can have the base voltage rating and current rating, but based on the taps, you're going to have a different voltage and current rating for each taps. Then on-load tap changer rating, right? Okay, so for the on-load tap changer rating, right, you can have let's say plus or minus 16%, right? So plus or minus 16% itself tells you 33 tap position for the on-load tap changer. The on-load tap changer means that the transformer taps usually for an LC transformer, those taps are located on the low voltage side. It means that the tap the tap changer can be changed while the transformer is in operation. Right? Okay, so plus or minus 16% means that you can have 33 taps. Okay, so for the energized tap, it's usually plus or minus 2.5%. Next is the vector configuration. Right? So the vector configuration. So for a delta Y transformer, right? Okay, so you can have a D, Y, and 1. Okay, so the vector phase shift is about 30 degrees. So it means that the high voltage side leads the secondary side by 30 degrees. Okay, so if you have a DY 2, then it means that similarly, it means that high voltage leads the low voltage side by 60 degrees. So basically, this configuration is based on the blocking system. Right? 1 means 30 degrees, 2 means 60 degrees, just like a clock. Okay, so next is the winding configuration. Okay, so if you have a delta winding configuration on the high side, or Y ground, Y solidly grounded, Y resistor grounded configuration on the low voltage side. Next is the weight of the transformer, right? Okay, so you can also have the weight of the whole transformer itself, and the weight of the oil itself, and the number of gallons of oil. That is very, especially the number of gallons of the oil is very important, because it helps you to calculate whether your transformer containment, can contain the amount of oil, if there should be an oil spill, if that transformer should fail. And the weight of the transformer helps also the structural engineer to basically perform his analysis to determine if the foundation can still support the weight of the transformer. Next is the manufacturer, the year that the transformer was manufactured. Yeah, because if you have a 50-year transformer, that itself basically tells you that this transformer has been in service for a long time, and basically helps you with your analysis as well. And the manufacturer, basically, that also helps you. So that itself helps you to basically take a deeper dive, benchmarking into the industry to see if there's any problem with that transformer. Let's say number of failures. Basically, that helps you to look further into the industry to find out if this manufacturer, this type of transformer, is basically subjected to a lot of failures. Then next is the type of power transformers, right? You have the seal type, right? Okay, so the seal type transformer is basically is covered with basically you have a nitrogen blanket on top of the oil, basically that basically provides a cushion, from the oil, and basically prevents oxidative elements from the outside element from intruding into the oil. Next is a free breathing consider type. So that itself basically has a glucose device that is basically integrated to the piping system between the consider tank and the main tank. Next, as we show you, as I show you what should be on your inspection check sheet that you are going to use for your to perform your field data collection. I've made mention in the previous slide what data you need to collect from the nameplate of the transformer. So the goal is after you collect all this, you check that information with the OEM construction manual to see if what is there is what matches on the nameplate. The next is your bushing, right? Okay, so you perform a visual inspection of the bushing, right? Okay, so the goal is basically to see the level of contamination on the bushing, right? And you'll be surprised that a lot of this bushing has, especially if it is in an industrial facility, that is when you have a lot of dust and contamination there. And the type of bushing, right? As you know, we have basically polymer bushings, and basically we have porcelain bushings, and basically they all have their own advantages and disadvantages and attributes. Okay. So, and you also want to check if there's any condition monitoring device that has been installed on the bushing, and the information that the data and the parameters that it is providing. If you have a SCADA system or local HMI, you can also check for your C1 capacitance of the C1 rating. As you know, for this typical condenser bushings, right, that has capacity layers internally, right. You have a C1 area and a C2 area, right? So the C1 area is basically from the conductor, right, of basically of the transformer to an electrode that is internal to the bushing, and the C2 area is from that electrode to the tap point of the bushing, right? So you need to collect all this data, basically, and you can also, if the bushing monitoring is providing tan delta, that is power factor of the C1 region and the C2 region. You can also collect that information. Next is maintenance inspection and testing results of and the history of the bushing. Sometimes, um, testing is done separately for the bushing and, compared to the maintenance, and sometimes testing is done uh, both for the maintain and the bushing altogether. Then you also need to check your spare inventory that you have for the bushing. Like I indicated, at least on a minimum, you should have one bushing for the high side, also another bushing for the low voltage side. Okay, so that's very important. And also you want to check, the storage of the bushing. Manufacturers of bushings basically provide instructions on how this bushing should be stored. The goal is to have the oil all over those. It should be stored in such a way that the oil should be all over the capacitive layers. Right? Some of the capacitive layers shouldn't be deprived of oil, because what it is, it can create voids and pockets, and can basically result in partial discharge activity and failures when it is brought into service. Next is, if there's any maintenance and testing that is done on that spare bushing. Some of the utilities, periodically, perform inspection and testing of the spare bushings whilst they are in inventory status. Next is, like I indicated, if you have any condition monitoring in place, you can obtain that data. Next is on-load tap changer, right? Okay, so what it is basically you want to obtain a visual inspection of the on-load tap changer. Are there any oil leaks? And also if there's any condition monitoring that is in place. And some of the condition monitoring that basically are in place for all of tap changers is basically it monitors the motor current of the tap changer, and also the contacts current and voltage as well. Next, maintenance inspection and testing results of the on-load tap changer. Then the current tap position indication. And you can, collaborating with operations, so you can check the operational history of the tap changer, right? Okay, so because the manufacturers provides basically allowable tap changing number of tap changing sequence that you're supposed to have within the certain time period, right? Okay, so if the on-load tap changer has experienced a lot of tap changes within the setting, and it exceeds what the manufacturer tells you, that itself calls for further analysis. So that is when you need to basically collaborate, check with your protection unit and other stakeholders, operations, maintenance, and have a meeting with them and basically bring it to the attention of what you have observed, and the need to adjust the bandwidth of the voltage regulator. Because you know that the on-load tap changer operates based on a bandwidth of a voltage change. And so it's possible that the bandwidth is so tight, so that is causing that frequent tap changing. So it requires realization of the bandwidth setting of the voltage regulator. Next is the energized tap changer. We also want to provide the current indication of the de-energized tap changer. Okay, so next is performing inspection of the control cabinet as part of the inspection and check sheet. So for the control cabinet, like I indicated, your goal is to basically perform an internal visual inspection, and the goal is to check the condition of the seals of the doors. Because if you have a 30-year, 40-year, 50-year transformer that has been in operation for that longer period of time, and especially in a high humidity area, or basically extreme environmental conditions or harsh environmental conditions, what happens? Basically the door seals basically degrade over time, and the other thing is basically with high humidity, basically it forms a condensation on the thermal flux, and when it forms that condensation, it can result in basically shorting of the terminal wires and can cause the transformer to trip. So those are some of the things that you need to pay attention when you're performing inspection of the control cabinet. You also want to make sure that there's no wire that is loose on any terminal block. So basically, you want to physically check all the wiring, check for looseness of any wiring, and identify it as much. Next is your radiator, right? Okay, so for the radiator, the radiator, for a transformer, sometimes encounters a lot of leaks. Basically, your goal is to perform a complete round check from top to bottom of the radiator to basically identify leaks. And one thing that you can do is basically on your inspection checklist, just give a sketch, write a sketch of the location of the leak. If you identify any leak, just draw that sketch and basically mark where the location of that leak is. Because what is the reason why I'm saying that? It helps the one that basically if the leak has to be further fixed by the maintenance and operation, it helps them to locate it quickly, and basically it will also help them know what you're talking about. And a lot of the leaks with radiators, has to be around where the butterfly valves are. As you know, for a radiator, the butterfly valves are located right at the top and the bottom, because that is where the oil from the transformer enters the radiator, hot oil. After convection action, it rises to the top and basically through the radiator. The radiator takes the heat away, basically, and so the cooler oil comes down and it goes through another butterfly valve back to the main tank. Next is the grounding piece. Most often than not, power transformers, are grounded through grounding cables, and usually the minimum that I've seen is 2 grounding cables at diagonal side of the transformer tank. So basically, one at each corner going to the ground grade. Right? So you want to inspect all these the condition of these grounding cables. And for bigger transformers, I've also seen about 4 grounding cables. Right? So the goal is basically depends on the grounding philosophy that the utility company is implementing. And also to split the ground currents. Because as you add more grounding cables, basically you're providing much more lower resistance to the ground grade. Next is the oil leaks. So I indicated that power transformers, usually after 25, 30 years in service, most often than not, that is when leaks becomes prevalent, and becomes problematic. So some of it, you just have to manage it, unless of course, the leak is excessive. So some of the major concerns with leaks is with bushing. Bushing leaks, that has to be taken serious. Right? That's very important. Yeah, but the main tank, if it is a minor leak, you can basically manage it. But if it is a major leak, you need to pay attention to it and make a note of it. And sometimes, the drop rate of the leak can be noted. Let's say every second, every minute, you can note that leakage rate and put it down, and also note the location by just a sketch where the leak is located, so that it helps with planning. Let's say if an upcoming outage, major outage is coming up, basically you can arrange. If it is a major leak, you can arrange for that leak to be saved. Next, it's a neutral grounding resistor, right? And this actually applies to most industrial facilities, where the neutral of the Y grounding side of the transformer. The Y grounding side, mostly it's the low voltage side, and the delta side is the high voltage side. Okay. So, What you want to do is basically perform a visual inspection of the neutral grounding resistor. A lot of times, what I've seen is, there's a lot of compilation of dust on the grounding resistor. So you want to make sure that check to see, and basically the condition of the dust. If it is a lot, you also want to indicate that, because what it does is it helps with the planning piece, where you provide an indication for planning, basically, to and the maintenance crew to take a note of it. If an outage opportunity comes by, basically they can take advantage of that and leverage that and basically perform the cleaning of the dust that is located on this grounding resistor. Next is inspection and testing results of the grounding resistor. Usually, it's insulation resistance testing that I've seen, and basically testing to validate the resistor, just to make sure that the resistor value has not drifted. So these are the typical testing that I've seen on grounding resistors: the insulation resistance testing and the testing of the resistance itself. Next is the auxiliary devices, right? Okay, so you have for a power transformer, you have auxiliary devices that are basically mounted all over the peripheral of the power transformer. So you have an oil temperature gauge, okay, or oil temperature indication, okay, right? Okay, so what you need to do is perform visual inspection of it, okay. So in performing the visual inspection, you want, on the glass of the oil temperature indicator, you want to make sure that the readings are legible. You can see, so because sometimes if you have a power transformer that is located in a very extreme or harsh environment, the surface of the glass basically becomes very corroded, and basically it's very difficult for you even to see the indication of this oil temperature gauge. Then you also want to verify the first stage cooling, second stage cooling, alarm, and trip point as per the manufacturer's manual. So that itself requires a close collaboration with your protection unit, and to verify that basically the set points are basically based on what the manufacturer recommends, or your protection unit recommends. Next is your winding temperature gauge. So similarly, just like the oil temperature gauge, you want to make sure that you perform visual inspection to make sure that the glass is clear and all indications basically can be seen from the ground level, and also the set points for the alarm and trips per the manufacturer's manual. Then again, on this oil temperature indication and the winding temperature indicators, right? Okay, so you have basically the current indication in the maximum indication. The maximum indication is usually indicated by a red indicator sticker. So you want to make sure that that is reset, because as that indication that you see over there is basically the last time maximum value that has been shown by that indicated by the transformer. So you want to make sure that the operators at this point basically reset that value. Next is the oil level gauge, right? Okay, so basically on the oil level gauge, you perform a visual inspection similarly to make sure that they are visible from the ground level, and basically the set points for the alarm and trip level is better by the OEM. Then you have to check the oil level gauge in the meantime, and the tank. And sometimes you can have an oil level gauge in an on-load tap changer as well. Okay. So for the solid pressure device and the pressure relief device, a lot of these devices basically their problems with oil leaks as the transformer ages. So that is one of the things that you need to pay attention to. And the last testing results, basically, what they do is during major outages, basically this solid pressure device and pressure relief device are tested to make sure that the micro switches basically activate and basically perform the required alarm and trip as is supposed to. So next, we'll move to containment for oil spill. Okay, so as you know, for a power transformers basically sits on a concrete foundation, and basically to perform this inspection, you need a structural engineer, a specialist that can help you to do the assessment. So the goal is basically to perform an inspection of that foundation and basically the containment. So around the containment, basically you have gravels that is supposed to basically contain the oil if there should be a spill. So basically, like I indicated, it's a structural engineer that helps you to do this assessment part. Next is the foundation, and basically the foundation. So like this also basically you need a structural engineer to take the position of the foundation. Because as a power transformer sits on the foundation for 40, 50 years, sometimes cracks develop in this foundation. And as you know, these transformers are very massive with a lot of weight, the active component and oil. So to support, continuously support that weight, you need basically a resilient foundation. This foundation that won't compromise with cracks, right? Okay, so that's why you need that assessment to be done by a structural engineer. Next is our verification of a firewall. Okay, so if you have at a substation facility, you have more than 2 or 3 power transformers in close proximity to each other, right? Very, very important that basically, I think more than I think the spacing, if I recall, is about 9 to 10 meters, right? If it is less than that, I think it requires a firewall. So that itself, you need to make that measurement and basically determine if a firewall is needed. Similarly, the distance between the transformer and the substation building, that also needs to be measured, and make sure that the substation building is firewall ready. Okay, so you have done all your field inspection, field data collection. Okay, you have obtained all your documentation, maintenance records, inspection records, planning documents, operational records, OEM documentations, right? 1 lines, 3 lines, okay, schematics. Then that is when basically you perform the assessment itself, right? Analytics and interpretation of data, right? Again, it's the criteria, right? Okay, so a typical example is, let's say, if you have performed, you are evaluating and maintenance electrical testing for the transformer, right? Okay, so you are evaluating the turns ratio of the transformer, right? Okay, so you evaluate that turns ratio against the nameplate, right? Or the last time the transformer was tested to see the delta, the change, right? And that itself has to be evaluated with a criteria of plus or minus 0.5%. Next is the insulation resistance and polarization index, right? Okay, so for a typical transformer like that, I'm expecting newer transformers. I'm expecting insulation resistance of gigaohms range. But for a service age transformer, let's say more than 20, 30 years, then basically more than 100 ohms, right? Okay, so same applies to the polarization index, right? Okay, for a new transformer, I'm expecting a polarization index of 2.0, greater than 2.0. And a service aged transformer, more than 30, 40 years, then I'm expecting between 1.5 to 1.5 and above, right? Okay, so yeah, because as the transformer ages, right, you're not going to get it as perfect as newer transformers. So this is a typical example of how we evaluate those criteria. You evaluate what the current testing results with what the criteria is supposed to be. Next is testing of the capacitance, right, of the main tank and the bushing and the turn depth or the power factor. Okay, so basically you evaluate the capacitance, high voltage to ground capacitance, low voltage to ground of capacitance, high voltage to low voltage capacitance against what is on the nameplates and the factory acceptance testing results. Very, very important. So that itself will tell you if there's a significant change in capacitance. That itself will tell you that the insulation system has deteriorated, right? Or there has been a change in arrangement of the insulation system. Next is the time delta, the power factor of the insulation system. That is both thermally upgraded paper and oil, right? If the power factor is greater than 1, then that itself tells you that there's a problem inside with contamination and moisture intrusion, right? Okay, because for a newer transformer, I'm expecting a power factor of about 0.5%. Service age transformer about 0.5% to 1%, right? So these are typical examples of how you evaluate your criteria. Next, bushing testing results. Okay, so you evaluate what is the maintenance practice with basically the criteria, the capacitance C1. You basically determine what was measured with what is on the nameplate, and the power factor, what was measured with what is supposed to be, should be between 0.5 to 1%. For a new transformer, about 0.5%. Okay, so these are just a few examples of how we evaluate the maintenance testing results against benchmark criteria and determine basically corrective actions that needs to be done. Okay. So after that, when you complete all the analysis, and basically you then digitize all your field data records and start writing your report. Okay. So you write your report, and the appendix part of your report will be all the data that you collected in the field. Right? So you're gonna, let's say, if you did it for 2 or 3 equipments, you're gonna have appendix A, appendix B, appendix C. Then you're gonna have a attachment appendix D for your maintenance records, inspection, testing records as well. Then if there's any pertinent, important OEM attachment, manual attachment that needs to be attached, that you can also do it. Next, it's once you finalize the report, right? Next is basically scheduling. You send the draft of the report to all stakeholders, right? Right from upper management through discipline engineers, operations, maintenance. Then basically for them to take a look at what is in the report, all the gaps that were identified when you performed your reliability assessment, and the corrective actions that were identified, and whom the corrective actions will be assigned to, and the timeline that is required to perform these corrective actions. So you send that to them for them to, and give them, due date for them to complete the review. I would say that on a weekly basis, send them casual courtesy reminders. So I would say on a ballpark, you can give them about a month to review such a report. And part of it is what you can also suggest to them is, on their side, on the proponent stakeholders side, they can organize a meeting, and they can collectively review your report. It makes it easier to, it makes it basically, it makes it easier for them to basically review your report and provide comments to you. So once I basically you receive the comments, then you can schedule another meeting with them to basically review all the comments that they provide until you all come to a common agreement with the full content of the report and the corrective actions that needs to be implemented. Whom the corrective actions will be assigned to, the due dates of the corrective actions. Next is basically implementing a tracking system for the corrective actions. Because what it is, you don't just assign corrective actions to individuals, just leave it like that. You need to track it. So let's say you have corrective actions. Some corrective actions can be completed within a very short time. Let's say within a month, 3 months, 6 months, a year, depending on the degree of gap, how extensive that gap is. So that itself will dictate the due dates, the length of the due dates for these corrective actions. So, that is something that you need to pay much more attention to when basically you are driving this and basically tracking these corrective actions. And also to send them, casual reminders, especially those that the corrective actions are assigned to, and remind them. You can also have a KPI system of tracking these corrective actions, where basically you send basically visualization of corrective actions that has been completed, the ones that are in progress, the ones that have exceeded. If any of these corrective actions have exceeded, first of all, you need to do due diligence. Basically, you shouldn't wait for the due dates to exceed, but about a month or weeks before the due dates, you need to visit with the individual, have a meeting with the individual, have them know that the reason they need to complete these corrective actions before the due date shown. And sometimes there's a need to extend these due dates for these corrective actions due to the workload on these proponent stakeholders. So that itself requires further discussion. So basically, you can work with the individual to extend the due date. With that brings the end of my presentation. Thank you so much for your listening ears. And basically, if you like this presentation, select the like button in YouTube, and also subscribe button on YouTube. Thank you so much. And basically, look forward to the next presentation that I'll bring, and that is performance condition assessment. Okay, so condition assessment is the second step after the performance reliability assessment. Thank you so much.